Greetings and welcome, friends. Mr. Waddy here today. Yesterday we talked about making lines of best fit based on a scatter plot, based on some data, and trying to represent that data with a line, if possible. And if I want to determine how well my line represents the data, this is one of the ways I can do it. It's called a residual. Okay? And so a residual, it says, is the difference of the y value of a data point and the corresponding y value found using the line of best fit. So what's going on here? So let's look at this picture. So here's my data point, right? Here's one of perhaps many. Here's another data point right here. I have my line that represents this, Ethan. It's inappropriate. So here we go. Here's a line of best fit. I would have some model that represents this. I could use this line to predict a value, and I would then compare the actual value to the predicted value. And if I subtract those two things, that number is called a residual. All right, that's what a residual is. If a point is above the line, that's a positive residual. If a point is below the line, then from my predicted value, that would be a negative residual. And if I look at all of the numbers, all of these distances, I'll be able to determine whether or not my line represents the data well. So a scatter plot of the residual shows how well the model fits the data. If the model is a good fit, then what's this mean? Absolute value of the residuals are relatively small. Yeah. I'm not sure. When we were talking about functions? Yes, that functions have to pass the vertical line test. Notice my line is a function, but it is possible to have multiple points of data that have the same multiple outputs for the same input. So Ethan, this is like a zoom in on the graph. That's what someone just asked. Shouldn't the line kind of be like this to hit those data points? Imagine there was more data points to the left or the right. Nope, we would draw a single equation that represents it. So here we go. Example 1. In example 3, yesterday, we might have had the equation y equals negative 20x plus 20 that modeled this data, okay? So if I have y equals negative 2x plus 20, we'll do this on paper first, and then we'll do this digitally. And here, stop playing with my books and follow along, gentlemen. So let's find what these residuals are. This is how this works. So everyone's writing this down on the paper. Find the y value of the model. So what this means is I'm going to plug in 1 for x. So negative 2 times 1 plus 20, what is that equal to? No, we're going over today's lesson 4.5. Plugging in 1 for x, my model would tell me, right, negative 2 times 1 is negative 2, plus 20 is equal to 18. Now to find the residual, I'm going to take the actual and minus my predicted. Yeah. Okay. Just under example 1, you can that's fine. You can just add it to it. All right. So yeah, you can just add a couple columns in there. Good catch. I'll have to fix that later. 19 minus 18 is 1. So this residual is 1. Is 1 kind of close to the line? I don't know. We'll have to look at some more of them to see how well it's doing. So let's find another residual. So negative 2 times 2 plus 20. That's negative 4 plus 20 is 16. And if I want to find the residual, I'm going to take the actual number from my data, which was 15, and minus the predicted number, which was 16, and I get negative 1 this time. So there's another residual. Now, the smaller these residuals are, that means the more close my line was at predicting the data. Let's do one more, and then we'll do it digitally. So negative 2 times 3 plus 20. Negative 2 times 3 is negative 6. Plus 20 is 14. And now let's subtract these. So 13 minus 14. I don't know. Let's find out. So, oh, these ones are dropping by 2 because the slope of this was negative 2. But let's take a look at this data. And let me show you how to do this on a spreadsheet. And then I'll show you how to do this on Desmos. So here is example 1. So make sure you have example 1 selected. And in this cell, it says, right, Y value from the model. And this is going to be perhaps one of your first equations you've ever written in a spreadsheet, and I'm so happy that I get to be here with you. We're going to start by typing an equal sign. You guys already logged into this using the hyperlink on the front page of your packet, and then you made a copy of it. Did you click on example 1, the tab down here? Does yours say 4.5? Yeah? Let me come check. Guys, we're typing in our equation. If you're not there, you can follow along, and you'll be able to practice during the class quest. So, equals. Now, what was my equation? It was y equals negative 2x plus 20. So watch this. I'm going to do y equal sign, no y, equals negative 2 multiplied. Do you guys know how to multiply in a spreadsheet? You use the little asterisk right above the 8. So shift 8 will give you a little star. And I want to multiply this by x. Now in my case, x is over here in column A. And so I want to take negative 2 and multiply by this 1 over here. I'm actually going to click in this cell. And notice that it says A2. Let me come around and see how you guys are doing. All right, so let's see. Then our y-intercept was plus 20. So I'm going to write plus 20. And if I hit enter, Ethan, gentlemen, it gives me 18, which is, notice what I got right here when we did it by hand. Okay, now let me show you a cool trick. Because I told this formula to reference this x value, I want to copy this formula to these other cells. One way you could do that is actually Control-C or copy it and paste it. And notice it actually is now referencing the next cell. I could also just Control-C and then select the whole thing and hit Control-V to paste it. But an even cooler way is if I select this, either of these, down on the lower right of that rectangle is a square. And if I move my cursor over it, it becomes a black plus sign. And I'm going to click and drag until it is highlighted there. And when I let go, it duplicates the formula all the way down. And notice that if I click on one of these, it's actually referencing the different x value every time. All right? Did everyone get that to work? So we can actually see it basically filled this column for us. Did you write in the equation equals negative 2a2 plus 20? Yep. All right, for the residual, how did we calculate the residual? We took the actual and subtracted the predicted. So over here, I'm going to make a new formula. I'm going to hit equals, so the spreadsheet knows it's a formula. I'm going to say take this B2 and minus C2. And if I hit enter, it tells me the residual is 1, which is what I had there. Did you do B2 minus C2? And do you have an 18 or a 0 in that column? And then you can drag that formula down. Oh, it might be like, yeah, a little bit. Sometimes formulas can be slow. Yep. So I clicked B2 minus C2. I could type that, or I can do it by clicking on the cells, which I feel is kind of a nicer little bit of interaction. Let me come check. All right, gentlemen, let's go. Now, let me show you how I can actually graph these residuals. And this will actually tell me whether it's a good fit. So watch this. I'm going to highlight this column, and holding control, highlight this column. Gentlemen, be quiet. And having just those two selected. Guys, how did I select just those two columns? I have to hold control. So I highlight one, hold the control key, and highlight the other. That can be a little bit tricky without a mouse, Ethan. And once I have both of those selected, let's insert a chart. And we're actually going to graph the residuals here. Let's see, scatter plot. Yep. And under chart types, I scroll down to select scatter. And these are not my data points, these are my residuals. And if I insert the chart, that's what this actually represents. This is my residuals. And I see I've got roughly the same number above as I do below. So that means it kind of represents this okay. All right, let's check out Desmos. I want to show it to you this way. So if you didn't keep up with the last one, here's your chance. Click on the hyperlink for Desmos. Here, Cameron, stop making noise. Yeah, you click it, and then it shows up underneath, and you click again. So here's Desmos. So you click on the cell, and then eventually underneath it, the hyperlink shows up. Right? Everyone in Desmos. Good. All right, so here's my function. And if I want to figure out the residuals for this, click down on your table here, and just to the right of y1. Now notice I conveniently named my function f of x instead of y equals. And one of the ways I can have this formula work out is if I write f of, in parentheses, x1. And notice now it fills this column. And what's it doing? It's taking these x values and plugging them in for x and telling me what the output is automatically. Click to the right side of that now. And I'm going to, in this column, I want to take my actual value and subtract my predicted value. So I'm going to write y1. It's upset about that for a moment, but that's okay. Minus f of x1. And it's got these points in green. And now if I click out of that somewhere on my graph, you can actually see the residuals are plotted right here. If you want to get rid of the second set of blue points, you could, but you don't have to. Now let's zoom in on those residuals. You can use the plus sign if you need to. And you can see that, right? Some are above, some are below. But there's 3 above, 3 below. That means the line represents the data pretty okay. Pretty okay. All right. Now it turns out your Desmos can actually make a best fit line. Remember how we made our best fit line earlier? Let's make that for this one. Click down at the bottom of your table and type y1 tilde forever. So underneath the table, y1 tilde, let's do mx1 plus b. So this orange line is actually going to be better than our blue line. And look at this information here. Tilde, yep, instead of an equal sign. Yeah, it's called a tilde. Basically, I'm telling the computer, make the graph such that it's approximately, is kind of what that symbol means, approximately mx1 plus b. It's on the top left of your keyboard. Yeah, does Desmos have that anywhere here? No, it doesn't look like they have it on their little... but guys, notice, what do I see in this information panel here that might help me out? Notice it says residuals right there, and it's got a button. Let's click plot. And what it does is it actually plotted in orange all of my residuals. And actually, this one was worse than the other function we had, but every other one is closer to the x-axis than the corresponding green dot. And that means that this orange line is actually better than the blue line that we had. Okay, so that's kind of, right, takes a little while to get used to. That's the big idea. So using residuals, we use them to predict whether or not our graph is a good model. And because there's about the same number above as below, they're doing okay. All right, let's go to, and you could have calculated this out by hand and plotted that, and it's a lot of work. Let's look at example 2. All right, so back on paper for a moment. The table shows the ages X and salaries Y in thousands of dollars of 8 employees at a company. This is the equation that models the data. Is the model a good fit? So if we go back to our spreadsheet and click on example 2. You guys with me? Example 2. I need 100% participation here. Example 2. Here's that same data. And we could do our formula thing again, but let's just jump right into Desmos. So click on that Desmos link. And that's going to be example 2, Desmos. All right. So here is the line. That's the equation they gave us. Here's the data plotted. Now looking at this, do you think that line represents that data great? Not terribly. It looks like that's almost a little bit more of a curve. And we'll actually see the same thing when we do the residuals. So let's do it with a table again real quick. Let's calculate what is f of x1. Oh dear. There we go. F of x1. So those are all the predicted values. And how do I find a residual? I subtract, right? I do the actual value minus the predicted value. So I'm going to write for this next column y1 minus f of x1. And those are my residuals. Now notice these numbers are off a little bit more than the last one. And notice that if I zoom out and I look at these green dots, I mean, I've got 1, 2, 3 below, 1, 2, 3, 4, 5 above, but it kind of makes like a mountain, right? The fact that there's kind of like a hill here, or even if there was a valley, would suggest that this probably isn't represented by a line, right? That a line isn't the best thing to represent this. And this is probably one where I could have had better residuals. Let's do this together. If I had a curve, and I'll show you how to do this, even though this is a little bit beyond what section we're in. So back over here on some cell, anywhere, it doesn't matter where you put it. Let's do y1 is approximately, and let's do ax1 squared plus bx1 plus c. And so this, notice this green thing actually matches a little bit closer. Doesn't hit all of them, and not that they ever hit any of them. But let's plot the residuals for this and see what we get. And notice that those are actually much closer to the line, and that they're kind of, right, more densely packed. That there's roughly 1, 2, 3 above, 1, 2, 3 below, yep. And it's not like a whole bunch of above in the same section and a whole bunch below in the same spot. That it's kind of like up, down, up, down, up, down, which is kind of what I want. I want it to be the average of that. So in this case, I would say in example 2 that it is not a good fit. All right. The model, oh dear, what did I do? Model is not a good fit. And our explanation would be that there were more points above than below for the residuals. Right, Adriana? Is your cell phone on the desk next to you? I don't know. Don't worry, I got it. Okay, all right. There were more points above than below, and the points were in a curve. Right, the points were curved. So I can use this to kind of analyze whether or not this is a good representation of the data. All right, one last thing we're going to talk about, which is that r squared I told you guys about. All right, so we're going to go down to example 3, but before we get there, I got to talk to you about a correlation value. Finding lines of best fit. Graphing calculators use a method called linear regression. That's the same thing that your spreadsheets, Excel, Desmos uses to find a precise line of fit called the line of best fit. A calculator often gives a value of r called a correlation coefficient. This value tells whether correlation is positive or negative. So if r is positive, right, then it's a positive correlation. The slope is positive. If r is negative, that means the slope is going down. But it also gives me kind of a decimal value. So it's not just about positive or negative. That the closer to -1 or +1, the stronger the correlation. And if it's like 0.26 or 0.1 or -0.3, the closer it is to 0, the weaker the correlation becomes. So let's look at this in action. We might actually even be able to revisit some of our other graphs as we do example 3. All right, so example 3, finding a best fit line using technology. This is about Old Faithful, the geyser. Actually, wait. We can actually look at, here's example 1. Notice the R value is -0.98. You can almost think about that as like a percentage. So like that means like you could pretend it's like 98% accurate. Okay? And it was also negative, which notice this had a negative correlation. Look at this this blue one here. Oh, no, I don't have the R value here. I can make that happen though. Let me get rid of that. And if I did y1, gentlemen, follow along, please, gentlemen. If I do this, notice this R value for the line, my purple line, is like 0.4. So that means it's like 40% accurate. It's not great. So that's why I could say that there's a weak positive correlation between these things. The R value is positive. So I kind of like pretending of the R value is like a percent, like I was saying. Let's take a look at example 3. About Old Faithful, we'll go to the Desmos graph. All right, so here's my data. Let's make a prediction. It looks like row 2 has some space. How do I make a prediction using their pre-made best fit line calculator, friends? Got my data in a table. How do I do it? What do I type? How do I get it to give me a best fit line? Y1. Anybody? Tilde. Yeah, we're doing a line. mx1 plus b. Okay. Yeah, so if I want to program this to find a best fit line based on some data that I copied and pasted or plugged in, this is what I do. I use the tilde. I reference my data points x1 and y1, and then it finds the best values of m and b possible. All right, now question, is this a good correlation? How could you answer that question? Yeah. Oh, that was when you were out of the room. You'll have to catch it later or read it in your packet. So 0.97 is the R value. What does that tell me? It's positive, so there's a positive sloped correlation. What else does it tell me? Is it strong or weak? 0.97, if I think about that like percent, I like to think about it as it's almost like 97% accurate. So that's a strong correlation. We can also determine that by, if I click plot residuals, and you can see that those are all pretty close, right, to the 0 there. Those are all pretty close. Now let's see, what do they ask us to do? Plot the graph, did it. Identify, interpret the correlation coefficient, did it. Positive, strong correlation. Interpret the slope and y-intercept. What does a slope of about 12 mean in this problem? So that the geyser will be, let's see, what was this? Time, let's see, duration in minutes compared to the times between the next eruption. That if as the let's see, as the time between eruptions increases by 12, the duration of the next eruption increases by 1 minute. All right, so that's what that would be referring to. And then you could make predictions that if for some reason there was a longer wait, if there was like a 10-minute wait, these are in minutes, we would expect a much longer duration. Nope, I read that wrong. X was the duration. So if it's a 10-minute duration, then it's a 155-minute wait until the next. There we are. All right, well, thanks for watching, Internet friends. Adios.